Let us continue Carnot cycle. In the Carnot cycle, we will see efficiency of a cycle. We will see efficiency of a cycle. We will see efficiency in the sense net work done by the system. We have to take net work done by the system. Net work done by the system by how much amount of heat we have transferred, that we have to take. So amount of heat transferred to the system. Like this we have to take. Okay. So efficiency of a cycle equal to net work done by the system by amount of heat transferred to the system. What is the meaning of this one? In the sense, suppose we are giving 1 liter petrol. Okay, this is called 1 liter petrol. 1 liter petrol we have given. 1 liter petrol we are giving means how much distance the vehicle moves. That we have to consider. So distance the vehicle moves and how much amount of petrol we have given. Okay, amount of petrol. For this amount of petrol, what distance the vehicle travels. That ratio if we take, that will give efficiency of the vehicle. Okay, so exhaust and all we cannot take. Exhaust in the sense that is waste only. Okay, so therefore 1 liter petrol we are giving in the sense how much distance the vehicle travels. That is called efficiency of the vehicle. Like this, in the efficiency of a cycle, Carnot cycle, net work done by the system we have to take. Net work done by the system in the sense that area in the cycle, area within the curve, area within the cycle. Okay, area within the cycle, that is net work done by the system. Then amount of heat transferred to the system. System is absorbing heat from the surrounding. That heat we have to take. Okay, so we have considered efficiency of a cycle. We got it. So now we will substitute the values. Net work done by the system. That we will substitute. Okay, so net work done by the system in the sense minus W total. Net work done by the system in the sense minus W total we have to take. Amount of heat transferred to the system in the sense in the first step, system absorbs heat from the surrounding. That is Q2 symbol we have taken. In the first step, isothermal reversible expansion of ideal gas. In that system absorbs heat from the surrounding. That is a Q2 symbol. That Q2 we have given. Okay. Next we will write this minus W total we will substitute. Minus W total is how much in the sense NR ln V2 by V1 into T2 minus T1. That we can write. By Q2 we will substitute. Q2 in the first step we have written Q2, that is how much in the sense NR T2 ln V2 by V1. Okay, what are the common things that we will cancel? So NR we are cancelling, then ln V2 by V1 we are cancelling. Then what is the rest in the sense T2 minus T1 by T2 is the rest. It is called what in the sense efficiency of a cycle. So efficiency of a cycle is equal to T2 minus T1 by T2. Then here minus W total is equal to what we got in the sense Q2 plus Q1 we got. Minus W total is equal to Q total. Minus W total is equal to Q total we have written. Q total in the sense Q2 plus Q1. It is first step heat involved is Q2. Third step heat involved is Q1. Rest of the two steps adiabatic Q is equal to 0. Okay. Therefore, Q2 plus Q1 is minus W total. This Q2 we have written. This is called the efficiency of a cycle. This efficiency of a cycle we will substitute here. Therefore, we will get to what in the sense Q2 plus Q1 by Q2 is equal to T2 minus T1 by T2. Like this we can write. Okay. This we will simplify. What we will get, we'll see. So 1 plus Q1 by Q2 is equal to 1 minus T1 by T2. Okay. So what is cancelling in the sense? One is getting cancelled. So one is getting cancelled. So what is the rest in the sense? Q1 by Q2 equal to minus T1 by T2. Okay. This we can write it as Q2 by Q1 equal to minus T2 by T1. Then we will write Q2 by T2 is equal to Q1 by T1. Like this we can write. Then we can write Q2 by T2 plus Q1 by T1 is equal to 0. Okay. Now this indicates Q by T is equal to 0. Q by T is equal to 0. That means why we have written Q by T is equal to 0? Q by T in the sense this Q by T is equal to 0. Q2 by T2 first step. Q1 by T1 third step. Second step and fourth step is adiabatic. Q is equal to 0. So that we are leaving. So Q for a cycle, T for a cycle, like this mean. This cycle is a reversible, therefore we will write a reversible. So Q reversible by T is equal to 0. Now we will take Q reversible by T is equal to 0 for a cyclic process. Q reversible by T is equal to 0 for a cyclic process. Cyclic process in the sense initial state and final states are equal. For that cyclic process, Q reversible by T is equal to 0 in the sense Q reversible by T is a state function. It is a state function. So for this state function, thermodynamics, in second law of thermodynamics, one thermodynamic term is introduced. That thermodynamic term is called a delta S. Entropy change we can say. Delta S is called entropy change. Okay. So delta S we are taking. Delta S is called what in the sense? Entropy change we can say. So now see Q reversible by T is equal to 0 for which in the sense for Carnot cycle. For Carnot cycle we are saying Q reversible by T is equal to 0. We are saying this is for a cycle. For a cycle in the sense initial state is equal to final state. So this is equal to 0 in the sense this Q reversible by T is not depending on the path of the process. It depending on initial state and final state. Since initial state and final state are equal, the Q reversible by T is equal to 0 for a cycle. Therefore, this Q reversible by T is a state function. For this state function, second law of thermodynamics introduces thermodynamic term that is called delta S. Delta S is called entropy change. So remember that delta S is equal to Q reversible by T. Okay. So delta S is equal to what we can say means Q reversible by T. This is introduced in the second law of thermodynamics in order to describe spontaneity, in order to give criterion for spontaneity. Why second law of thermodynamics is introduced? Why second law of thermodynamics is developed? What happened to the first law of thermodynamics? First law of thermodynamics also giving thermodynamic term, no? First law of thermodynamics also giving criterion for spontaneity, no? When first law of thermodynamics gives criterion for spontaneity, what is the necessity of second law of thermodynamics? Is there any limitation of first law of thermodynamics? Yes. In the first law of thermodynamics says for spontaneity delta H is equal to negative. First law of thermodynamics introduces a thermodynamic term delta H, enthalpy change. Enthalpy change is equal to negative for spontaneous process. That is criterion for first law of thermodynamics. But many endothermic processes are spontaneous. Many endothermic processes are spontaneous. First law of thermodynamics is unable to explain that. First law of thermodynamics says that exothermic is a criterion for spontaneity. Exothermic means heat is liberated. That liberated heat drives the reaction, drives the spontaneous process. So driving force is what in the sense delta H is equal to negative. That's what first law of thermodynamics says. But for endothermic evaporation of water, it is a spontaneous process. For that, how do we say? So first law of thermodynamics unable to say. So first law of thermodynamics criterion term is not wider. First law of thermodynamics criterion term for spontaneity is bounded to certain area only, not for all the spontaneous process. So in order to overcome the limitation of first law of thermodynamics, second law of thermodynamics introduced. In that, what is the thermodynamic term introduced in the sense of delta S? That delta S is equal to what in the sense Q reversible by T. Okay, so delta S is equal to Q reversible by T. Understand that entropy is a state function. Entropy is a state function. How first law of thermodynamics, thermodynamic term internal energy enthalpy is state function, like this entropy also a state function. Sir, now what is the unit of this entropy? We'll see. This entropy unit is a Q unit is a calories we can say, or joule we can say. This temperature in the sense Kelvin. So like this we are saying, therefore calories per Kelvin, joule per Kelvin, like this we can say. Okay, next we will go for a, we will say delta S for ideal gas in terms of temperature and volume. Okay, we are taking ideal gas. For ideal gas, we are saying this delta S in terms of temperature and volume, we will say. Okay, now we will take first law of thermodynamics. First law of thermodynamics mathematical form is delta U is equal to Q plus W. For infinitesimal change, what we can say means du is equal to dq plus dw. For infinitesimal change, we can say like this. Then we will substitute this dw. Du is equal to dq minus p dv. P dv. P is called pressure of gas, we can say, because it is for infinitesimal change. Infinitesimal change in the sense it is possible for reversible process. For reversible process, external pressure is equal to pressure of gas, we can say. Sir, next step. We are taking next step. So du is equal to this dq reversible. This dq reversible. Pressure of gas we can write it as nRT by V. We can write pressure of gas. We can write it as nRT by V. Sir, next this we will divide this whole equation by T. We will divide that whole equation by T. Therefore, du by T is equal to dq reversible by T minus nr dv by V. dv by V we have written. Du we will substitute. Du is called ncvm dt. Du is called ncvm dt by T. Then dq reversible by T is called ds. dq reversible by T is called ds. S is called entropy minus nr dv by V. Now we will do some interchange. We will do it. So on interchanging ncvm dt by T plus nr dv by V. Now it is for infinitesimal change. For entire change, what we have to do means we have to integrate it. Initial temperature T1, final temperature T2. We have to integrate it. Initial volume V1, final volume is V2. Like this we have done integration. Now this delta S or ds also will integrate. Initial entropy is S1, final entropy is S2. This ds on integration gives what in the sense entropy S. For this initial lower limit is S1, upper limit is S2. Okay. Next, this ncvm is constant. The constant will take ncvm is constant that we have taken. Then we will take this dt by t. We will integrate it. dt by t we will integrate it. dt by t on integration gives ln t. Lower limit t1, upper limit t2. Then plus here nr is there. That nr constant term we will take. nr constant term we have taken. Next, dv by v is there, that we are integrating. dv by v on integration gives ln v, lower limit v1, upper limit v2. Okay. Upper limit we will substitute s2 minus lower limit we have substituted n cvm Upper limit will substitute ln t2, lower limit will substitute ln t1 plus nr. Upper limit will substitute ln v2, lower limit will substitute ln v1. Okay. S2 minus S1 we can call it as a delta S, that is equal to n CVM. This ln t2 minus ln t1 we can write it as ln t2 by t1 plus nr. Ln v2 minus ln v1 we will write it as ln v2 by v1. Like this we will write. Now, the delta S is said in terms of temperature and volume here. N is constant number of moles. CVM is called molar heat capacity at constant volume, that is constant. T2 is temperature variable. R is universal gas constant. Volume is variable. So we said delta S of an ideal gas in terms of temperature and volume. This is for ideal gas. Understand that this is for ideal gas and also for reversible process. For reversible process. Okay. So we said delta S in terms of temperature and volume. If you take volume is constant, if you take volume is constant, this term vanishes. Therefore, delta S is equal to what in the sense n CVM, n CVM ln T2 by T1 we can say. If volume is constant, if we take volume is constant, V2 by V1 is 1. Therefore, this term vanishes. Therefore, what is there? N CVM ln T2 by T1 is there. If you take volume is constant. Suppose if you take temperature is constant, T2 by T1 is cancelling, therefore this term is vanishing. So what we will get means delta S is equal to nr ln V2 by V1 we will get if temperature is constant. Okay. So if you take temperature is constant, then we can say delta S is equal to nr ln V2 by V1. Okay. So when you take temperature constant, delta S is equal to what we have to say means nr ln V2 by V1 we can say. If you take volume is constant, then we can say delta S is equal to mCVM ln T2 by T1 we can say. Okay. Next we will say delta S in terms of temperature and pressure we will say. Delta S in terms of temperature and pressure we will say. Okay. We are saying delta S in terms of temperature and pressure. Now we will take this equation. This equation will take delta S is equal to n CVM ln T2 by T1 plus nr ln V2 we will substitute. V2 we will substitute as nr T2 by P1 P2. Okay. V2 we are substituting as nr T2 by P2. Then this V1 we will substitute. V1 will substitute as nr T1 by P1. Okay. V1 we have substituted as nr T1 by P1 because ideal gas. Okay. What are the common terms that is cancelling? You see, nr getting cancelled. Okay. Nr getting cancelled. So what is the remaining? Okay. So delta S is equal to n CVM ln T2 by T1. Delta S is equal to n CVM ln T2 by T1 plus nr ln T2 P1 by P2 into T2 by T1. Okay. P1 by P2 into T2 by T1. nr ln T2 by T1 into P1 by P2. Like this we have written. Okay. So yeah, this nr ln T2 by T1 into P1 by P2. Like this we have written. nr ln T2 by T1 into P1 by P2. So next we will write this n CVM ln T2 by T1 plus nr ln T2 by T1 plus what we can write means nr ln P1 by P2 we can write. This T2 by T1 into P1 by P2 we can write it as like this ln T2 by T1 plus ln P1 by P2 we can write. Okay. Then here ln T2 by T1, here ln T2 by T1 is there, take it out commonly. Here n is there, here also n is there, take it out commonly. So n we are taking out common. Ln T2 by T1 also we are taking common. So what is there means CVM plus R is there, that we have written. Then this nr ln P1 by P2 we have written. Then this n CVM plus R we can write it as CPM. CVM plus R, we can write it as CPM. What is CPM means? Molar heat capacity at constant volume. CVM in the sense molar heat capacity at constant volume. It is at constant pressure. Cp means constant pressure. Cv means constant volume. Ln T2 by T1 we can write plus NR ln P1 by P2 we can write. This NR ln P1 by P2 we can write. This ln T2 by T1 we can write. Now it is a delta S in terms of temperature and pressure. Okay, here delta S in terms of temperature and pressure is given. In the previous case, delta S in terms of temperature and volume is given. Okay, so delta S in terms of temperature and volume we will see. Okay, so now we will see delta S in terms of temperature and volume. Okay, that formula we will see. What is that formula? Delta S in terms of temperature and volume means NCVM ln T2 by T1 plus NR ln V2 by V1. That we will write. Okay, so NCVM ln T2 by T1 plus NR ln V2 by V1. Okay, it is in terms of temperature and volume we said. Okay, now we will compare these two delta S. It is in terms of temperature and volume. It is in terms of temperature and pressure. Here in both cases N is there. Here CPM, here CVM. Here ln T2 by T1, here also same. NR, ln. P1 by P2, but V2 by V1. Volume is inversely proportional to pressure. That's why like this. Okay. Here pressure is there, therefore Cp. Here volume is there, therefore Cv. Okay. So delta S in terms of temperature and pressure here, it is delta S in terms of temperature and volume. Sir. Next, we will see what is meant by entropy. Entropy means what? That we will see. What is meant by entropy? That point we will see. Entropy, the term, this term is introduced in order to measure what means randomness. In order to measure randomness. Entropy is a term which is coined in order to measure randomness or disorder. Randomness or disorder. Okay. So entropy is a term that is measuring what in the sense measuring randomness. Otherwise we can say disorder we can say. Okay. So entropy is measuring randomness in the sense when randomness increases or disorder increases, entropy also increases. When randomness or disorder increases, we can say entropy increases, we can say. So now we will take gas, we will take, and the liquid we will take. How the entropy is there? How the randomness is there? So gas and liquid in the sense, in which case randomness is more? Gas. So in which case entropy is more? Gas. So gas is having higher entropy than liquid. Then we will take solid, we will take. Liquid and solid we will take. In which case randomness of arrangement of particles, constituent particles you see. Randomness is more in liquid when compared to solid. Therefore, entropy of liquid is greater than solid. In the solid, we will take amorphous solid and crystalline solid we will see. Amorphous solid in the sense here particles arranged irregularly. Crystalline solid in the sense particles arranged regularly. So where randomness is more in the sense amorphous is having higher randomness than crystalline. Therefore, entropy is more for amorphous solid when compared to crystalline solid cell. Now, for a chemical reaction, how to write delta S? We have seen already enthalpy of a reaction we have seen. Like this, how to see entropy of a reaction. How to see entropy of a reaction. Entropy of a reaction, how to see delta RS. How to see entropy of a reaction. Say. For a reaction, how to say entropy of a reaction, that we'll see. Let us take equation. Now we are writing equation. Haber's process will take. Haber's process in the sense nitrogen combining with hydrogen to give what in the sense ammonia. It is Haber's process. For this Haber's process, what is the entropy of a reaction? For this reaction, what is entropy? That we'll see. Entropy of a reaction is equal to entropy of products minus entropy of reactants. Entropy of reactants, we can say. Entropy of a reaction. Entropy of a reaction is equal to entropy of products minus entropy of reactants. Now we will take a standard entropy of reaction equal to standard entropy of products minus standard entropy of reactants, we can say. Now we will substitute products. What is products in the sense ammonia? We will take S naught M ammonia gas we will take. What is the meaning of S naught M? Superscript naught is called standard, S is called entropy, M is called molar. So molar, standard molar entropy, S naught M means standard molar entropy of ammonia in gaseous state. That is the meaning of this. Molar in the sense for 1 mole, but here how many moles are there? 2 moles. So multiply this with 2 minus reactants N2 we will take. So for N2, S naught M N2 gas. Then H2 will take plus 3 into S naught M H2 gas. Okay, H2 gas we have written. 3H2. 3H2 means 3 times H2. Okay, this is called standard entropy of reaction. Standard entropy of reaction we have to write like this. Okay, so if equation is given, for that how to write standard entropy of reaction means like this. This entropy in the sense it is not only for gaseous state, even for other physical states also we can write. Okay, now what is the delta rs naught? What is the standard entropy of reaction? Whether it is positive or negative, how to see? Okay, here 2 times ammonia is there, here 4 times reactants is there. Reactants 4 times present, but ammonia present 2 times. Therefore, this delta Rs naught is negative. Delta Rs naught is negative because it is more number of moles. It is less number of moles. Therefore, delta Rs naught we can say negative. We can say, sorry, okay. We'll take some other equation. We'll take now hydrogen gas plus bromine liquid. Hydrogen gas plus bromine liquid gives a HBr gas. HBr gas we can say. Okay. Hydrogen gas reacting with a bromine liquid to give a HBr gas we can say. For that, how to say standard entropy of reaction? So standard entropy of reaction is equal to standard entropy of products. That is what means HBr. That is HBr. Okay. So standard molar entropy of HBr in gaseous state. In gaseous state, how many moles means 2 moles. That 2 moles we will write minus H2. H2 will write standard molar entropy of H2 gas plus bromine we have tried. Standard molar entropy of bromine liquid. Bromine liquid we have written. Okay. Now delta Rs naught is positive or negative or 0. Here 2 moles, products 2 moles, reactants also 2 moles. Products 2 moles present, reactants also 2 moles present. Therefore, delta Rs naught, what shall we expect? Shall we expect 0? We will check. Here, products 2 moles, that is gas. Reactants 1 mole, hydrogen is gas, but bromine is liquid. Liquid is having lesser entropy. Gas is having very high entropy. Therefore, this here entropy is more when compared to this entropy. Therefore, delta Rs naught is positive here. Delta Rs naught is positive, we can say. Okay. So why? Because gas is having very high entropy when compared to liquid. Liquid is having high entropy when compared to solid. So next, we'll go for a third law of thermodynamics. Third law of thermodynamics will go. Okay. Third law of thermodynamics we are taking. Sir. Now we are taking what in the sense 100% pure crystal will take. 100% pure crystal in the sense what is the percentage of impurity? How much impurity is there? Impurity is 0. Impurity is 0. No impurity is present. 100% pure crystal we are taking. That means impurity is 0. Is it possible practically? Certainly not. 100% pure crystal is not at all possible in the universe. Therefore, it is what in the sense in the ideal situation only it is possible. Sir, practically it is not possible. That is the meaning. Sir, perfect crystal will take. We'll take perfect crystal. What is the meaning of perfect crystal in the sense? Arrangement of particles. Arrangement of particles is perfect. Arrangement of particles is perfect. What is the meaning of arrangement is perfect means randomness is zero. Randomness is zero. That is the meaning. Disorder is zero. Arrangement is regular. Arrangement is perfectly ordered. Ordered arrangement. Perfectly ordered arrangement. Randomness is zero. Disorder is zero. That is meant by perfect crystal. Temperature how much means 0 Kelvin. 0 Kelvin in the sense kinetic energy is zero, because kinetic energy is directly proportional to temperature in Kelvin scale. 0 Kelvin in the sense temperature is zero, so kinetic energy is zero. Kinetic energy is zero in the sense no motion at all. No motion in the sense vibration, rotation, translation, nothing is there. If the situation is like this, then randomness we can say zero. Randomness zero in the sense entropy is zero. Entropy is zero. That's what third law of thermodynamics says. Third law of thermodynamics says entropy is zero when in the sense when the temperature is zero, when the impurity is zero, when the arrangement of particles in the crystal is perfect arrangement. At that time entropy is zero. This is called the third law of thermodynamics. Is it possible practically? Is it possible practically? Practically, such a type of situation is not at all possible. Ideal situation only possible. Sir. So, what is third law of thermodynamics? We have seen. Next, we will see phase transformation. We'll see. Next, we are taking phase transformation. Next, we are taking phase transformation. We'll take. Phase means solid phase, liquid phase, gaseous phase, like this. Transformation means solid is converting into liquid, liquid is converting into gas, like this. Okay. So one we will take a fusion. That is a fusion in the sense solid is converting into liquid. That we will take. This process we will take it as reversible process. For this, what is the delta S? For this fusion, what is the delta S? We will see. Delta S fusion, delta S fusion or delta S melting, delta S melting is equal to Q reversible by T. Q reversible by T. Q reversible is called delta H reversible, we can say. Delta H for this fusion, delta H for this fusion, for delta H for this melting. Okay, delta H by T. T is called what in the sense melting point. T is called melting point, we can say. T is called melting point, we can say. What is this delta H? This delta Hm is called what in the sense molar enthalpy. Molar enthalpy of a reaction. Reaction is what? Fusion. Molar enthalpy of fusion. Then delta Sm is called what in the sense molar entropy. Molar entropy of fusion. Molar entropy of fusion, we can say. Sir. M is called melting also, we can say. Next we will take vaporization. We'll take vaporization is liquid is converting into vapor. Vaporization in the sense liquid is converting into vapor. That is called vaporization. For vaporization, we can say delta S vaporization is equal to delta H vaporization by T. T is called boiling point. Boiling point, we can say. Next, we will take a sublimation. We'll take sublimation. We'll take sublimation in the sense delta S sublimation is equal to delta H sublimation by sublimation temperature we can take. Okay, so delta S sublimation is equal to delta H sublimation by sublimation temperature we can take. Sir, this is called a phase transformation. We have said, sir. Now, for what sake this delta S is introduced in the second law of thermodynamics? For what sake this delta S is introduced in the second law of thermodynamics? In order to overcome the limitation of a criterion of spontaneity by first law of thermodynamics. First law of thermodynamics is having limitation in the criterion of spontaneity. So to overcome that, only second law of thermodynamics introduced. In the second law of thermodynamics, delta S is introduced. So what is the criterion given by delta S for spontaneity? That we will see. What is the criterion given by delta S for spontaneity? That we will see. Okay. Now this delta S total, this second law of thermodynamics takes delta S total for giving criterion for spontaneity. What is delta S total? Delta S total means what? Delta S total means delta S system plus delta S surrounding. Delta S surrounding. That is called delta S total. The second law of thermodynamics considers system and surrounding, both delta S values. It considers sum of these two, it takes as delta S total. It gives criterion for spontaneity with the help of delta S total. Okay, so second law of thermodynamics gives criterion for spontaneity by taking what term? Delta S total. Delta S total means what? Delta S system plus delta S surrounding. Okay, so it says that delta S total is equal to positive is the criterion for spontaneous process, negative for non-spontaneous process, 0 for equilibrium, 0 for equilibrium. Like this, this criterion is set by second law of thermodynamics. So second law of thermodynamics says delta S total is equal to positive for a spontaneous process. Why positive for a spontaneous process? For spontaneous process, why should we say positive? Sir. Now we will take a natural process, we will take. Spontaneous process we will take. Natural process. Suppose you are dropping a drop of ink into the glass of water. What will happen? The ink starts distributing throughout the water uniformly till it attains uniform. You are dropping a drop of ink into the water. That ink, what it does, that ink itself starts distributing throughout the water till it becomes a uniform distribution. That means, see the spontaneous process, how the spontaneous process is there. It takes place by its own. Now, how the randomness is there, you see, how the randomness is there. Now we are taking here water, we will add a drop of ink, we added a drop of ink. We need not do anything. This ink itself, it itself starts distributing throughout the water till uniform distribution is attained. Yes or no? So what happens to the randomness in this process? Randomness goes on rising or not? This process, is it a spontaneous or not? This process is a spontaneous. This is a ink is distributing continuously throughout the water. That means what happens to the randomness of ink particles? Rises. Randomness of ink particles rises for this spontaneous process. Therefore, spontaneous process in the sense randomness increases, rising. Randomness increases. So whatever the spontaneous process you see, randomness will go on rise. In the entire universe, how the randomness will be there means